We'll do like some part of subgradients today. If we can finish it, great. If not, we'll continue next time. And this may all lead to us edging out a lecture on numerical linear algebra, but I don't feel so bad about that because we can always pick that up when we talk about the second order algorithms unit later. So it doesn't really need to happen now. So in other words, the schedule on the website, we may end up kind of a bit delayed compared to that, but it'll all work out. So yeah, so here's gradient descent, just to remind you what it looked like. We talked about this last time. We proved that this thing has a certain convergence rate. We talked about how to choose step sizes and all that stuff. So the algorithm is that we're given a function f that's convex and smooth, and we pick an initial point, and we just repeatedly evaluate its gradient at the current point that we're at, and then we move in the direction of the negative gradient multiplied by some step size over and over again until we converge in some sense. So that was gradient descent. And we talked about those things I just mentioned last time, convergence rate, step sizes. We talked about, right, so let me just remind you actually, so before we forge on here. So we had two different convergence rates that we kind of attributed to gradient descent under two different conditions, two different regimes. The first was a regime in which the function that we're trying to minimize is convex and smooth and has something called a Lipschitz continuous gradient, which you guys saw as part of the first homework and we've defined here. Just means that the gradient, whenever the gradient acts on two vectors x and y, the distance between those outputs is less than or equal to L times the distance between x and y. That's what it means for the gradient to be Lipschitz with a constant L. Under this regime, we proved in class that to get an epsilon suboptimal solution, to arrive at a point xk that has this property, right? The criterion value at xk minus the optimal value is less than or equal to epsilon, that we need on the order of 1 over epsilon iterations. Okay, so if you wanted to, for example, get a solution that was, had 0.1 suboptimality gap, then we need on the order of 10 iterations. If you wanted a suboptimality gap of 0.001, then you need on the order of 1,000 iterations. That's how you can think about it growing, right? Every time you ask for another digit of accuracy, you have to have another order of magnitude more iterations. That's what this convergence rate kind of roughly means. The other regime that we looked at was this guy, the strong convexity regime. So now our function is not only differentiable and has a Lipschitz continuous gradient, right? Here it says under the same Lipschitz assumption as before, and it's convex. We also assume that it's strongly convex. Okay, and we again talked about this quite a bit when we learned about convexity, and you worked this in your first homework, so there are many equivalent ways of thinking about this, but one way of thinking about it that's maybe particularly helpful with respect to the Lipschitz condition is that it implies that our function is lower bounded by a quadratic everywhere. The Lipschitz assumption, remember, implied that our function was upper bounded by a quadratic everywhere. That was, in fact, the first step of this proof that we used. Okay, this is kind of the other side. Tells us that our function is actually also lower bounded by a quadratic everywhere. So we can, in a sense, control how curved the function is around its minimum, right? If our function is lower bounded by a quadratic everywhere, then around its minimum it's going to be quite curved. So these two conditions together give us a much stronger convergence rate than what we had before. And the conclusion is that under strong convexity, the convergence rate is on the order of log of 1 over epsilon iterations. So much, much faster than on the order than order 1 over epsilon. Okay. We're going to visit second order methods in a number of weeks, and we're going to see that actually this convergence rate is even showed up by second order methods. So second order methods, for example, Newton's method under some conditions will achieve an even much faster convergence rate than that. Okay, so in terms of where this is on the grand scheme of things, this is pretty fast, but it's pretty fast for first order methods. Still, second order methods should be able to achieve this rate also. Okay, and then the important caveat we pointed out was that we can think about this in two ways, I guess. Order c to the k. So after k iterations, that's the error we see, where c is some constant less than 1. Or equivalently, if we want the error to be less than or equal to epsilon, the optimization error to be less than or equal to epsilon, we need log of 1 over epsilon iterations. And written in this notation, the important caveat we kind of remarked last time was that this constant c, it depends on the condition number of our problem. So we take the Lipschitz constant divided by the strong convexity constant. We call that the the conditioning number of our problem. It's also an upper bound on the condition number of the Hessian of our function everywhere, if our function was twice differentiable. And if this is very high, then our function is very poorly conditioned, which means that in some directions has kind of very extreme curvature. In other directions, it has much more flat curvature, loosely speaking. And those functions are harder to optimize. So if it has a very high condition number, this c is actually very close to 1. So even though this is going down like c to the k, it could be going down actually like not as fast as we may expect. And if you want to see a precise expression for c as a function of L and M, you can take a look at the Boyd and Vandenberg textbook. We also, I think, last year's homework or 2 years ago's homework, we have a homework problem where you prove this rate. Okay, the homework problem steps you through the proof of this rate, and it constructs the c value for you explicitly. So you can take a look at that also. Is there a question here?
So what do you mean by L over M being upper bound for a Hessian, which is a matrix?
For the condition number of the Hessian.
Oh.
So the condition number of a matrix is the ratio of its largest to its smallest eigenvalues. Okay. So then we went through this kind of rather quickly, but still went through this. What do these conditions mean for our for a very common problem that you might look at, which is when the loss is just squared error loss in regression. And we didn't go over this, so this is where I wanted to kind of pause and just mention where gradient descent fits into the grand scheme of things. So we didn't talk about stopping rules. I'll be very vague about stopping rules until we get to duality. When we get to our lectures on duality, we'll see that we can stop in such a way that often we can control the suboptimality gap. So we can kind of figure out how much we have to go until we have a guarantee like this one. Like if you gave me an epsilon ahead of time and you asked me, to optimize until you had an optimization error to within that epsilon, from this perspective, it's kind of unclear how to do that, right? We don't know what this is, so how do we know when to stop? So we're just going to say, at this point, you just stop when the gradient is small. Okay, when the gradient is small in norm, then that's probably a decent stopping rule because the gradient should be 0 at the solution. When we talk about duality, we'll talk about how to control the duality gap, which we'll see in turn actually gives us guarantees like this one. So we'll be able to kind of deliver much more precise stopping rules later in the course. Okay, and where does gradient descent fit into the grand scheme of things? So here's some of its pros and cons. It's rather simple. It's a very simple idea. And each iteration is usually cheap compared to, let's say, second order methods, certainly, which we'll talk about a bit later. So that's good. It can be fast for well-conditioned problems and problems that are strongly convex. A disadvantage is that it can often be slow because many of the problems that we want to solve in practice aren't actually strongly convex or they're poorly conditioned. Okay, so a lot of times, for example, in problems like these ones, right, where if we're looking at high-dimensional problems where this X matrix has, say, more columns than rows, then we saw as part of this kind of, brief analysis here that we can't have the Hessian being non-singular in such a case, which means that our function is actually not strongly convex. So in several interesting cases, it's either poorly conditioned or it's just not strongly convex in the first place, so gradient descent may not be that fast. And maybe an even bigger disadvantage is that as we define it, we can't handle non-differentiable functions. So we just don't know what to do if f wasn't smooth. Okay, so we'll treat this one kind of right away. This one we'll kind of treat in stages. So we'll certainly see second order methods which will kind of, be the answer to, in a sense, poor conditioning. But we'll also see ways to speed up gradient descent as part of this unit, like acceleration, which will help just kind of in general. So we'll address both of these downsides in the course. Okay. I also went through this rather quickly, but I think it's actually quite an important result, so I'll just repeat it. And it's not very hard to prove. This was on the homework from a few years ago. We gave you some help in proving that a few years ago, but the proof is, say, about as long as the proof of the gradient descent convergence rate that we did in class. And it's a very kind of important statement to keep in mind. So the statement is roughly as follows. If you give me any initial starting point, okay, in any iteration, and the only restrictions that the iteration number we're looking at can't be bigger than about the dimension of your problem divided by 2. Okay, so you can't be asking kind of arbitrarily far down the path of these iterative algorithms. Then I can find for you a function such that any first order method cannot do better than this value in terms of its suboptimality gap. So in a sense, this is saying that if somebody writes down for you an algorithm that has a bound like this, okay, its suboptimality gap is less than or equal to something over k squared for all problems, then that's optimal, because no method can do better than that. Right? This is a lower bound on the convergence of all first order methods. So what we saw was that actually gradient descent was for all problems, that are in this problem class of convex differentiable functions with Lipschitz gradients, it had less than or equal to something over k, not something over k squared. So it had an upper bound that was actually quite a bit weaker than this lower bound. So now the question is there something that does better than gradient descent? Is there something that actually achieves this? Or was this actually just kind of loose? Right? For example, this is a lower bound. Something over k to the 10th is also a lower bound. Okay? So I could always kind of, think of lower bounds that are smaller than this. Is this one tight? Is there actually a method that achieves this convergence rate? It's a very fundamental result of Nesterov from the 80s. And the answer is yes. There actually is a pretty simple method. It's a modification of gradient descent that achieves a bound like this of something over k squared. And now that we have this lower bound, we know that it's actually optimal. So once we write down accelerated gradient descent, we know that essentially nothing can outperform it, at least in terms of rate. Some things can outperform it for some problems in some instances, but in terms of its kind of convergence rate over this whole problem class, accelerated gradient descent cannot be outperformed in some sense. Okay, so it's a very interesting and important sense of optimality. So we'll cover that in a few lectures. So as for now, I guess we just have in mind that gradient descent is doing pretty well, but it's not the best we can do. Okay, I thought it'd be fun to talk about gradient boosting, because this is kind of a neat connection between gradient descent and machine learning. How many people have seen gradient boosting before? Can I get a raise of hands? How many people have not seen gradient boosting ever? Okay, so much more people. So I think I'll go decently slowly, just because it's a nice connection. So let's suppose we're in a situation where we have observations, y1 through yn, and some predictor measurements, x1 through xn. We could be thinking of a setting in which these are continuous, and so we're trying to do something like regression. Or these could be discrete, and we're trying to do something like classification. Either setting is fine to keep in mind here. But the kind of unique thing about this setting that we're thinking about is that we don't actually have a typical model in mind for how, let's say, the mean of y should relate to these x's. In linear regression, we think about the mean of y being a linear function of the x's, right? And then we optimize something like this guy. We minimize something like this guy in order to get a linear function of the x's that predicts y well. In this setting, we don't think about a linear model being appropriate. We don't think about it sort of like a polynomial model being appropriate. We don't actually write down a typical model in any sense. But we think of a very, very general, flexible, nonlinear model for how y should relate to the x's, how the mean of y should relate to the x's. And here's what this model says. Our predictions, which I'm calling u, so these things are going to be, ui is going to be our prediction for the mean of yi. We're going to model it as being a linear combination of trees in our variable x. And each tree is going to look something like this. Okay, so each tree, when it's passed in a vector x, let's think about how x acts on actually xi, just so the notation isn't super confusing for you guys. Vector. And each tree is going to be basically having a bunch of sequential decisions that it makes at each of its nodes. It doesn't need to be a balanced tree either. So for example, the decision that it makes at the top node could be whether or not, let's say, xi5, whether the fifth component of my x observation is less than or equal to some value. Let's just call it, 1.2. And if that's true, we'll traverse the right branch. If it's not true, we'll traverse the left branch. And then here I might be, deciding whether or not xi, let's say 7, is less than or equal to, 29 or something, etc. So each of these nodes represents a decision, and we basically move appropriately down the tree depending on whether or not this was met at the observation. And at the leaves of the tree, we just make simple predictions. Like here, we'll predict that y should always be, about 5 or something. And here we'll predict that y should be like 6 or something. Okay, so at each of the leaves, we make just constant valued predictions. And this is just one example of one tree. Here I've written down all possible trees of a given depth in our variables. So here, that means that at every possible node, I can decide to split on one of p variables. And I can also decide to put any numbers I want at the leaves. So the size of this space is enormous, right? In fact, if we let these be continuously valued, then this is infinite. But let's suppose we actually restrict ourselves to predicting discrete levels at the leaves of the tree. Then this is enormous. It's like exponentially large, right, in the depth. So this is an enormous set of predictors that we're kind of allowing to model our mean, and we're allowing ourselves to take linear combinations of these things, okay, and arbitrary linear combinations. So it's a very flexible model for the mean of y given x. I'd say gradient boosting is maybe one of the best off-the-shelf prediction engines people use in machine learning. It's very common, or it used to be at least, and maybe at this point it's been upstaged a bit by deep learning, but gradient boosting I think still is extremely common as a black box prediction method. But as we've written it down, it would be essentially impossible to optimize. Right? Let's suppose I actually want to, I'm going to fix a loss function, like I'll fix squared error loss, because I suppose my y's were continuous. And I want to find the parameter vectors beta that minimize the loss between my observed y's and this linear combination of trees that I'm trying to form. Okay, because the number of possible trees here, which I've written as capital M, is just so enormous, this is essentially impossible to optimize, even for kind of smallish problems. Just because there are so many possible options for these trees, right? It's just too hard. So even though, let's suppose L was convex, even though this would be a convex problem because my parameters are beta, right? Here I'm having something just like a convex function of a linear function. Even though it could be convex, it's just too big to optimize. So what gradient boosting does is basically it runs gradient descent on this loss function, but it forces at every stage my predictions to be trees. So it's a very kind of clever way of running gradient descent. So the first thing that we do is that we think of my optimization instead of of this form, we think about it as minimizing just some loss, some function f over the predicted values. Okay, remember the predicted values were each of these guys was just ui. So I parameterize according to my n predicted values rather than my m coefficients, right, where m is enormous. M is the space of possible trees. N is the size of my data set. So it could be, however large my data set is. But then I have a restriction that u has to come from a sum of trees. So I haven't written that into this problem, but I'm really minimizing over all possible predictions I could make, subject to them coming from an additive sum of trees, which is kind of like a weird constraint. So here's what gradient boosting does. We start with a single tree. We can call that tree T naught, and initial predictions just to be equal to what comes from that tree. And then we're going to repeat basically gradient descent over and over again on this loss with respect to this variable, but at each stage we're going to kind of move back to the space of trees as appropriate. So here's how we do it. We first compute the negative gradient, at the latest prediction, our latest guess at what my mean of y should be. Call that uk minus 1, just per the usual notation. And here's what the negative gradient looks like. I'm just differentiating the loss function with respect to the parameters, and that's the gradient. And I've called it d for direction. It's the negative gradient. Then, instead of actually moving the direction of d, which I would usually do in gradient descent, right, I usually would add something like t times d to u. I find a tree that's close to, that should say d. Don't know why I said that. Sorry, it's a typo. So I find a tree that's close to d. So instead of doing uk equals uk minus 1 plus t times d, as I would do in the usual gradient descent, I actually do this. Plus t times a tree. Make sure that my update direction is a tree. And if I make sure this is true at every stage, then what I get at the end of this is going to be a sum of trees. Exactly what I wanted. So therefore, we have to find a tree that's close to d. Which is the negative gradient. That's the basic idea behind gradient boosting. Right, just run gradient descent, and every stage, instead of moving in the direction of negative gradient, move in the direction of a tree that's close to negative gradient. So how do we do that? We basically search over all trees and find the one that's closest in squared error loss in terms of how the evaluations it makes over the predictor measurements to that direction. This is not hard to approximately solve a single tree. So we can't even solve this exactly, but we can solve this greedily. Right? If you give me like a bunch of predictions I want the tree to make, then I can try to optimize over each split one at a time in a greedy fashion. And that's very common. People often call that CART to that algorithm. Okay, so I find a tree that's pretty close to that direction. And then these are my updates. Okay, I take uk to be uk minus 1 plus a step size, here I've called it alpha k, times that tree, the tree that is close to the negative gradient. And exactly as we asked for, our predictions are weighted sums of trees. Okay, that's gradient boosting, yeah.
Can you get out the convergence of the trackers?
It's a good question. I guess it depends in what sense you mean convergence. So almost assuredly not, that this is going to converge to the tree that actually, the sum of trees that actually minimizes this, no. That's maybe too much to ask for in some sense because this space is so big. But if you ask for something like, do you converge to something whose test error is good or whose test error is close to optimal? So not with respect to my loss in the training data, but to held out data, then there's a bunch of theory on gradient boosting that says that, yeah, it comes pretty close to doing that. It's a good question. Yeah, another question. I mean, you think about basically just taking, we're not actually kind of doing some, I'm not talking about trees in some geometric sense, like adding them. I just mean you take a bunch of trees and you have coefficients that multiply against them. Okay, and each of these trees, you know what to do. Let's suppose we ran this for r iterations. Each of these trees, if I gave you a value x and I asked you what would it predict, you know what to do. So you just evaluate each of these trees at x. It sends it down its tree. It gives you a value at the leaf. And you add up a linear combination of those predictions. Yeah. If you didn't have trees here, suppose your favorite thing, this is usually called a weak learner in the context of boosting. Suppose your favorite thing in the world was like a one-layer neural net. That was your favorite weak learner. Then you could do the exact same thing with a one-layer neural net. Nothing would really change. Right? All I'm asking for now is that instead of my predictions being a weighted sum of trees, they're going to be a weighted sum of one-layer neural nets. If instead of one-layer neural nets you loved some other weak learner, you could plug that in as well. So gradient boosting is really a framework for how to do what's called functional gradient descent. So doing gradient descent where there's some restriction on actually what the parameter space is, that's kind of an odd one. And at every stage, we just move instead of moving in the direction of negative gradient, move in the direction of the best thing in our space of weak learners, the closest thing in our space of weak learners to that negative gradient. Okay, hopefully that wasn't too confusing. It's not really fundamental to optimization in any way, but I thought it was kind of interesting from the ML perspective. So feel free to come talk to me if you wanted more details about that. Okay, the last bit on gradient descent that I definitely wanted to get to was stochastic gradient descent. We'll revisit this, I think, twice after this in the course. So you'll see this in a few different ways. So this is also a very kind of important, modern, relevant topic, just like gradient boosting. And it's to set the stage, we're considering minimizing a sum of functions rather than thinking of f of x is just some kind of generic black box function. Suppose it takes this form. It's the sum of fi of x over all I from 1 to m. And m, you're thinking here in your mind, is very large. So what are some examples of such a setup? Well, just think about, for example, the least squares loss, right? I can write least squares loss as the sum of yi minus xi transpose beta squared, I equals 1 to n. And this is the ith row of x. I can think of each of these as fi of beta. So really, I'm minimizing a sum of functions of my parameters. And if the number of observations is large, then I have a very large sum. This is just going to be generally true about most problems that we approach in statistics and machine learning. It's usually, if we think about minimizing something like the empirical version of the risk, then this is going to be a sum of something over data points. Same would be true in, say, logistic regression, right? So what we usually do in gradient descent would be we take the gradient of our objective function, and of course, just by linearity, right, of the gradient, that's just the sum of the gradients of the FIs. And so this is the step we'd repeat over and over again. Every time we want to update our parameters, we would take where we were, subtract off a constant times the sum of the gradients of these functions at the current point. But if m is large, like if I have, say, like 100,000 or 100 million or a huge number of data points in my data set, then this is very expensive to compute at each stage. It's a sum over very many things. So stochastic gradient descent essentially replaces this by, in the language of stochastic gradient descent, an unbiased estimate. So it really just takes, in the simplest form, just one term in the sum. So instead of, sorry, that was a bit confusing. I didn't tell you what this g was supposed to be. Gik is just the gradient of the function fik at x. Okay, so I just choose one of the functions in my collection. I choose some ik between 1 and m. I evaluate the gradient at that function, and instead of adding up the gradients from all the functions, I just take that function to determine the direction in which I'm going to move. It's like a very simplified version of stochastic gradient descent. It's the simplest form. Okay, so maybe I'll just be clear here. G ik at step k minus 1 is the gradient of the ikth function evaluated at x k minus 1. Okay, evaluated at this point, x k minus 1. So there's two rules for how to choose these this index I. Right? I just choose, in the simplest form, one index per iteration. And they are the cyclic rule and the randomized rule. So the cyclic rule, I just pass over my data points one at a time, and I let each of the functions that correspond to those data points, say in regression, tell me in which direction I should be moving. Okay, so I just iterate or cycle over 1 through m, etc. The randomized rule is I just choose one of these uniformly at random. This is much more common in practice, the randomized rule. it's usually more, well, it's more common in practice because I think it has theory that we can prove about it that's stronger because the theory is kind of averaged over this rule. So it's not really a worst case analysis, it's more like an average case in some sense analysis. And so people maybe tend to like the randomized rule because it has stronger theory associated with it. Plus, it's I think in practice it's just a good idea to incorporate this kind of variability to kind of smooth out over worst cases that you might expect. So let's ask ourselves the question, what's the difference between taking one stochastic step, so taking one step like this, or rather m stochastic steps, so m steps like this, and one step like this. This is usually called a batch update in the context of stochastic gradient descent. The usual update we call a batch update because you take kind of all the functions and you evaluate the full gradient. So first of all, computationally, what's the difference between doing m of these in a row and doing one of these? Is there any difference computationally? It's not supposed to be a trick question. There's no difference because I'm just evaluating the gradients here, right? I have to evaluate m of them, and I'm adding them up. Here I'm doing the same. Okay, if I do m of these steps in a row, I evaluate each of these gradients, and I add them up. Okay, so not a really big difference computationally. What about the progress that you make? Okay. Right, you're not, so that's what we're going to talk about here. So what about the progress that you make after m steps? So for simplicity, I've written down the cyclic rule, just so we can think about that. It's a bit simpler to think about in this setting. So m steps of the cyclic rule look like this. Okay, after m steps, I'm going to end up at a point that I'll call xk plus m. If I started at xk, and I've added up the gradients, basically, of each of my functions at the kind of relevant point, which is xk plus I minus 1. So when I'm at xk plus 1, I'm evaluating the gradient of my first function at xk. Right? Then I update, and I'm at xk plus 2, and I let my second function's gradient determine which direction I'm going to move in. So it's evaluated at xk plus 1, the most recent point, and so forth. That's what's being reflected here. Okay, at every iteration of stochastic gradient descent, right, the iterate changes. If I look at the one step of the batch method, then I can write that as xk plus 1. That notation is not so important, right, which is xk minus, again, a sum of m gradients, but they're all evaluated at this initial point xk. Okay, so the progress is in principle different between stochastic gradient and the batch gradient method. And I'll kind of hold off on precisely what the convergence of stochastic methods are. We'll revisit that in a couple of lectures. But now let's just look at the difference in the update direction. Okay, gradient descent uses this direction. And rather, the gradient descent direction minus the stochastic gradient descent direction looks like this. Right? That's the difference between the gradient descent direction and the stochastic gradient descent direction. So we can see that if somehow each of these functions doesn't have a gradient that varies wildly with x, then the difference in these directions maybe shouldn't be drastic, and SGD should converge. Right? What's the condition actually that we can place on this that we've actually already seen so far that would guarantee somehow that this is small? Think about what we've already used, what kind of conditions we've already used. I think I heard someone say it. Right, Lipschitzness, right? If each of these was Lipschitz, then this would be less than or equal to, say that Lipschitz constant Li times the distance between these. And then these might be small, just based on some kind of iterative analysis. Okay, so we can definitely see some way, maybe at least some path to proving that SGD should converge, because their update directions maybe isn't that different as long as the step sizes are small enough, and these don't have wildly varying gradients, these functions fi. Okay, so the kind of rule of thumb, though, is that stochastic gradient, which actually uses the most recent point, right, if we think about it over m cyclic updates, it does really well far from optimum. So it has great progress at the start. You initialize the point x0, stochastic gradient super cheap and it makes great progress. But it struggles kind of close to optimum. Okay, to get really fast convergence when you're kind of already close to the optimal value, stochastic gradient descent's not really going to do that. It's going to bounce around a bunch around the optimum. And we'll revisit this in a few lectures and talk about some of these convergence properties rigorously. But I just wanted to give you a sense for what these things would look like. Let's see. Okay, one last question let me pose to you. Even if, so computationally it's about more or less the same, right? M cyclic updates or M randomized updates are about as expensive as one batch step. Even if we can prove that the progress was about the same, that somehow this was quite small, why might it still be worth it to use stochastic gradient descent? There's still one aspect that could actually be really helpful. Even if after M steps we kind of had the same computational complexity as we would with batch gradient, and even if I'm telling you the progress was the same, why might it still be helpful to use SGD over gradient descent? Memory, yeah, that's a very important aspect we really haven't discussed so far, which is that if n is enormous, right, then actually evaluating this, over and over again may actually be difficult in the sense that we would need to somehow get all the points in memory. Especially if we're doing the randomized rule, then we can just be reading into points in memory kind of as we need them, right, to make these updates. Okay. So that was it, all I wanted to talk about on gradient descent. And let's skip over to subgradients. Okay, so we already covered all this. And this is the jumping off point, just to give some subgradients of the jumping off point to kind of overcoming this limitation of gradient descent. So gradient descent requires our function to be differentiable. We're going to learn something called subgradients today, which kind of extend, in some sense, the notion of a derivative to a function that's nice. So convex is sufficient condition for a function being nice for it to have subgradients. And we're going to learn kind of, after this lecture, how to use those to optimize a convex non-smooth function. Yeah, question? Do people switch from doing stochastic to batch? Not that I'm aware of. I mean, usually when you're using stochastic gradient descent, you're in a situation in which the batch method would just not run because the number of data points is so large, or because M in this notation is just so large. So it's usually not feasible to run batch gradient descent. People kind of usually throw their hands up, though, and say that if you're close to the optimum and stochastic gradient descent is not converging but bouncing around, then you're kind of close enough. And maybe in terms of, if your goal was to find a parameter in a regression or something, then what you end up at might be a good parameter. It might give you good test error, even if it doesn't kind of minimize the training error. That's more of the typical logic that people use with stochastic gradient descent. One thing you could do that's more concrete is just make the learning rate smaller. For example, the step size. You could just make the step size smaller. I'm close to optimum and bouncing around. You could, yeah, there's lots of kind of other things to do to ensure better conversions. And towards the very end of the course, we'll talk about something called fast stochastic methods, which do have much better convergence than this guy, but are still stochastic in nature. So, good question, yeah. Yeah, it can be. It definitely can be. Even if things aren't differentiable at one point, those points may be things that we visit often in the context of a minimization procedure. It could be, right? It depends on, like if we're setting coefficients to 0 or something as part of the lasso, then you might, depending on the method that we're using, an iterative method we're using, then we might be looking at points that are often 0 over the course of the algorithm. Components of our parameters are often 0. Okay, so this rest of today's lecture, and then however long it takes us to finish subgradients, is not about an algorithm. It's actually kind of stepping back just for a second and learning a mathematical concept that is extremely useful, both for optimization, kind of practically, and also for analysis when we talk about optimality and duality later. So let's just jump right into the definition. So if you remember, for a convex and differentiable function f, we saw that a necessary and sufficient condition for it to be convex, actually, if we had a differentiable function f, was that it satisfied this condition, that the linear approximation to my function, the tangent line, basically, to my function at any point x, is the global underestimator of my function. So f of y is bigger than or equal to f of x plus the gradient at x transpose y minus x. Okay, if f was differentiable, then it was convex if and only if this condition held. A subgradient, okay, if you give me a convex function f, then a subgradient of my function is just any vector g that takes the place of the gradient and makes that kind of the analogy of that expression true for all y. Okay, it's any vector g that that produces the following result: f of y is bigger than or equal to f of x plus g transpose y minus x. So just in one dimension, right? If my function was a function of just one variable, that at any point, all I have to do, even my function is not smooth there, have to just find one value of the slope, such that if I were to draw a line through the point, x comma f of x, so this is x, this value is f of x with that slope g, then that serves as a global kind of under approximation to my function. It lies below my function everywhere. So this always exists. Okay, here I've said f is convex. Subgradients always exist. It's a very nice property of convex functions. There's kind of a technical asterisk to put here, but I won't kind of dive into that unless maybe somebody, if you're curious, you can ask me, on the side or in my office hours. They cannot exist in some very pathological situations on the boundary of the domains of functions, but we don't have to worry about that. They pretty much always exist. If f is differentiable, then there's only one subgradient at x, and that's its gradient. Okay? We know that at least the gradient is going to be a subgradient. And if f is differentiable at the point x, then there's actually only one that makes that true. And in fact, the same definition is going to work for a non-convex function. Even if I didn't put convex up there, the same definition would work for a non-convex function, but subgradients need not exist. Okay, I don't always need to have subgradients, even for differentiable non-convex functions. So who can give me an example of a non-convex function that's smooth but doesn't have subgradients? Or at least at some points doesn't have subgradients. Right, that's a really good example. Okay, that function does not have subgradients anywhere. And I cannot find a single value of a slope parameter around which I can draw a tangent line that underestimates the function. Okay, this function's concave. You might object to that example. So functions like x cubed, right, they don't have subgradients, for example. Okay, so let's go through some examples of subgradients. How about the absolute value of x? So one-dimensional function, f of x is just the absolute value of x. So we can think about subgradients in kind of three cases. The first case is when x is strictly positive, in which case there's only one subgradient, and that's 1. Okay, you can think about that in a few ways. One is pictorially. Okay, if I'm out here and I want to draw a tangent line to my function that underestimates my function, that can only have slope 1, right? Because the function is just linear with slope 1 when x is positive. So certainly that's all I can do. You can also think about it from the point of view of this property, which I told you, if you have a function that's differentiable at a point in convex, then there's only one subgradient, and that's its gradient. So the absolute value of x is a convex function. It's differentiable when x is positive. Its derivative is 1. That's the only thing the subgradient can be. So likewise, when x is negative, the subgradient at any point x which is less than 0 is just minus 1. At 0, it gets kind of interesting. The subgradient is any element of the set minus 1, the interval minus 1 to 1. So I can draw a line with slope anything in between minus 1 and 1 that passes through the point 0, 0, and that's going to be a global under approximator to the absolute value function, right? It's going to lie below the absolute value function everywhere. You can also check that this definition is met for the absolute value function at 0 if this is anything, if this g is anything in between minus 1 and 1. Okay. All right, let's jump up in dimension. Let's think about the function that goes from Rn to R. That function is just the L2 norm of x. Here's a picture of what the L2 norm looks like in 2 dimensions, so when n is 2. When x is not 0, then this is actually, this function is actually differentiable, and its subgradient is just its gradient. Okay, the gradient of this function at a point x is not 0 is x divided by its 2 norm. So if you kind of remind yourself why that's true, you can also write out what this looks like in terms of the component functions, in terms of the components of x, and just differentiate with respect to x1 and then x2 and x3 and form that vector, and this is what it will be. Okay, so that's what the subgradient looks like away from 0. At 0, the subgradient is actually any element of this set, the set of all points z that have 2 norm less than or equal to 1. Okay, I'm going to leave this as a question on your homework to verify that this is indeed a subgradient of the 2 norm at 0. So you just go back to this definition and you ensure that when I take g to be anything that has norm less than or equal to 1, that definition is met. And conversely, if this definition is met for a particular g and for all y, then that particular g has to have L2 norm less than or equal to 1. Okay, that would be the way that you prove that. Okay, the L1 norm of x is also another interesting function. Here's what this looks like in 2 dimensions. So this is actually not differentiable at 0, but it's also not differentiable along any coordinate axis as well, unlike the L2 norm, which just has a single point, the origin at which it's non-differentiable. And really, actually, the story here is the same as the story here in, for the absolute value function. We just treat things on a component by component basis. So remember, the subgradient is a vector g. It's an n vector. Let's talk about each component of the subgradient. So when xi is not 0, then the ith component of the subgradient is unique, and it's given by the sine of xi. Okay, that's just for the same reasons as it was true for the absolute value function. When xi is 0, then I can take the ith component of gi to be anything between minus 1 and 1. Okay, that's the subgradient of the L1 norm. So it's a vector, and the elements of that vector are either just the signs of my original point x, or they're anything between minus 1 and 1 if the corresponding entry of x was 0. I think this is the last. Yeah, the last example I have here is the max of 2 convex differentiable functions. So suppose I give you 2 functions f1, f2. They're convex, and I'm telling you that also they're differentiable. And let's consider the function that is the pointwise max of f1 and f2. So remember that this is actually a convex function. We saw that in our lectures on convexity and operations that preserve convexity. So we can again talk about the subgradient in 3 cases. When f1 of x is strictly larger than f2 of x, then the subgradient is just the gradient of f1 at x. Okay, in that case, f of x is just equal to f1 of x, and if I ask you for the subgradient of this guy, it's just equal to the gradient of f1 of x. Helps if you draw this picture. So let's suppose that I have 2 functions. Let's call this f2 and f1. And their max is given by this darker function. It's their pointwise max. And now I'm asking you for subgradients of this darker function, which is f, which is the max of f1 of x and f2 of x. So out here, if f1 of x is strictly larger than f2 of x, then subgradients are just given by the gradient, right, of f1. That's kind of intuitive. Out here, if I have f2 of x being strictly larger than f1 of x, then subgradients are just given by the gradient of my function f2. That's also intuitive. If I'm at the point at which these functions are equal, okay, in one dimension that's just 1 point, but here I'm saying for any x in general at which these two are equal, the subgradient of the function f at such a point is in one dimension anything between somehow the limiting gradient of f2 from this side and the limiting gradient of f1 from this side. So it's really anything, any such value like this. In higher dimensions, it's any point on the line segment that joins these two gradients. So in other words, g I can take to be alpha times the gradient of f1 of x plus 1 minus alpha times the gradient of f2 of x. It's any convex combination between those two gradients for any alpha in between 0 and 1. It's a subgradient. Okay. Again, I think this is something that you'll either prove in your homework or you'll prove something very close to this in your homework. Maybe a case where you have n functions rather than 2, or k functions rather than 2. So all of these just go back to checking the definitions, more or less, of the subgradient. But I think that the drawing pictures like we've done in the past several slides in one dimension at least are very helpful. Question?
These the only ones?
Yes. These are the only subgradients, yeah. And in all the slides I've characterized all the subgradients for these functions. Okay. I think it's probably helpful to take a few minutes break, a little earlier than we usually do, but there's no hurt in that. Why don't we take a few minutes break and then we'll come back and finish off what we can of subgradients. We went through a bunch of examples of subgradients and we defined what a subgradient was. Here's a bit more useful terminology. The subdifferential is just the set of all possible subgradients of a function at a point x. And we denote it like this. It's usually this partial operator, or you sometimes call it del. Del f at x is the set of all g for which, g is a valid subgradient of f at x. So in fact, what I've described for you in all these examples is a subdifferential. I've told you all of the possible subgradients at a point x. Some properties of the subdifferential. It's a closed and a convex set. And that's true even for a non-convex function. It's actually quite an interesting property. Again, let's just maybe spend a few seconds thinking about why that's true. So remember, this is the set of all g such that g is the subgradient of f at x. Suppose that x was, that's not a good notation. Let's suppose g1 was in the subdifferential, and so was g2. Okay, then let's look at this point. Let's look at that value. We're trying to prove that the subdifferential is, say, a convex set. Then we want to prove that if we were to take the inner product of this guy with y minus x, we were to add f of x to it, and that would be less than or equal to f of y everywhere. So if that's true for all y, then we would have proved that this is a convex set, right? Because I can take any convex combination of valid subgradients and I get a valid subgradient. So this is true because it's true at g1. It's true at g2. Right, and I can just multiply say this expression by alpha and this expression by 1 minus alpha, multiply the right and left-hand sides. Still true, because alpha and 1 minus alpha are both non-negative. Add them up, and I get this. Right, so that was just a very quick check that subdifferential was convex. And notice we didn't use convexity of f at all, right? For any function, its subdifferential is a convex set. It's non-empty when f is convex. We've been kind of saying f is convex, in all of the slides, the very first thing. So it's non-empty, provided that we're looking at convex functions, but it can be empty for non-convex functions. Right? We know that non-convex functions, even ones that are smooth, don't need to have subgradients. We've already said this property, but here's what it looks like in terms of the subdifferential. If f is differentiable at a point x, then its subdifferential has just one element, and that's the gradient. So it's the set containing the gradient. And conversely, if the subdifferential happens to just contain one element, if we prove that this is the subdifferential, then our function must be differentiable at that point, and its gradient is this value g. So there's some properties of the subdifferential. There's an interesting connection between subgradients and convex geometry. Remember, we learned what the normal cone was. It so happens that if we take the indicator function, suppose this is our set. This is our set C, and we take the indicator function as our function. Right? This is the guy that's 0 on the set and infinity outside of the set. Then it turns out that the subgradient of the indicator function at the point x, here we're assuming C is convex, so is this indicator function. It's just the normal cone of this set C at the point x. So set of all vectors G that maximize, whose inner product over the whole set C is biggest at x. Okay, so and if you think about this visually, if I take this point x and I ask what are the subgradients of this function at this point, then it's just the normal cone. It's all vectors that start at 0 and move in this direction. I've just drawn them, leaving from the point x for kind of so that we can visualize them better. Okay, so this might be 0. This is the point x. I've drawn here x plus the normal cone of C at the point x. So that's an interesting connection between the normal cone and subgradients. And the proof is like 2 lines. So we just need to look at this inequality, right? If we have a subgradient g, then it's characterized by this inequality being true for all y at the point x. And let's just consider 2 types of y. If y is outside of the set C, okay, then this guy is infinity. That's 0, right? That gives us absolutely no restrictions on g whatsoever, right? Those points don't contribute at all to kind of conditions that we must place on g in order for it to be a subgradient, because we have 0 being bigger, infinity being bigger than equal to 0 plus something, and that will always be true. If y is inside the point, right, then we just have 0 is bigger than equal to 0 plus g transpose y minus x. Rearranged, that puts the condition on g that we must have g transpose x being bigger than equal to g transpose y, right? Just move this guy to the other side, and now we see that must be true for all y and c in order for this to be true. So that's our proof that the subdifferential was just a normal cone. Okay, we'll revisit that actually in just a few slides. In principle, although not really in practice, this has huge implications for like what we can say about optimizing convex problems. Was there a question? Was a hand up earlier? No? Okay. There's a bit of a calculus of subgradients, just like there is with the usual multivariate calculus of gradients and such. But we're kind of a little bit more restricted in terms of what we can say. So here are some of the rules that we know in terms of how to kind of calculate subgradients of combinations of functions and so forth. There are others besides these, but these are kind of the most basic or the most useful ones. So the first is, the first two are maybe quite obvious. If we have, just a positive multiple of our function, then the subdifferential of, a times the function f, where a is just a constant that's positive, is just a times the subdifferential of f. So these are sets. So by this I mean I take every element of this subdifferential and I multiply it by a, and that gives me the subdifferential of af. Okay, the restriction that a is positive is important, right? Because if f were convex and a were negative, then af would be concave. So this wouldn't even be able to talk about subgradients. Addition, if I have two functions and I ask for the subgradients of my first function plus my second, then I just get that by adding their subdifferentials. This means I take every element of this set, del f1, and I add every element of that set, del f2. This is kind of our closest thing that we have to a chain rule for subgradients, but we think about it in terms of the inner function, the composition being an affine function. So if I have a function f and I have a matrix A and a vector b, and I compose f with ax plus b, and I call that function g of x, then the subgradients of g are A transpose the subgradients of f evaluated at ax plus b. So this is a set. It means I take every element of this set and I multiply the matrix A transpose by it, and that gives me the set of subgradients of g at the point x. This is exactly like the chain rule, right, for gradients. In fact, if f was differentiable, this would be the chain rule if I were to compose f with ax plus b. Okay, so this would give you the usual chain rule, as it should. And the last rule, really, this is just one version of it, and the next slide has a more general version of it, is subgradients of maxima of functions. And it extends this guy that we learned here for just two functions. So the first version we have here is it's stated for m functions, for just some number of functions. The pointwise maximum of fi of x, I going from 1 to m. Then the subgradients of f at the point x is, well, let's break this down because it looks maybe a bit complicated. First, we look at all functions that achieve the maximum at the point x. Okay, so these are the functions for which at the point x this is as big as possible. This is, it achieves f of x. It achieves the maximum. Then we take their subdifferentials. Those are sets. We take all the subgradients of those functions that are active, the guys that achieve the maximum. We take the union of all those subdifferentials. So we collect all of those subgradients. And then because the subdifferential is always a convex set, we take the convex hull. Right? If I just took the union of a bunch of subgradients, then that may not be convex, right? This is making that a convex set. And it turns out that that is actually describing for you all of the possible gradients, subgradients of f at the point x. So let's apply that rule back here. See that it gives us the same. I'll write on the paper so you can peer at it. So this is the rule we just learned. And what happens if I just have my f being equal to the max of f1 of x and f2 of x, where these are each differentiable? That's what we had back on this slide, right? Then this rule actually reproduces this one. Right? Because, well, let's just do two cases, and the third will be symmetric. If f1 is bigger than f of x, then at that x, there's only one I, right? So let's suppose we're in a region where f1 is the only function that achieves the maximum. So there's only one I that we're taking the union over. And because I told you, like, let's say f1 was differentiable, its subdifferential is just it's just the set containing its gradient. So this is just the set containing the gradient of f1. And then I'm taking just the convex hull of that, which is just giving me back the set containing the gradient of f1. So that's just this case right here. Right? In the case where there's only one I that achieves the maximum for these two functions, then there's only one subgradient, and that's the gradient. If I'm at a point where these two are equal, then actually, let's say this I ranges over both 1 and 2. Both f1 and f2 achieve the max. That's this third case. And then I take the subgradients, or I take the subdifferential of f1 and the subdifferential of f2. That's just the set containing the gradient of f1 and the set containing the gradient of f2. And I take the union of those two sets. So now I have the set containing the gradient of f1 of x and the gradient of f2 of x. And I take the convex hull. That's going to, according to this rule, that's going to give me the set of all subgradients of my function. And what's the convex hull of just 2 points? It's just the line segment, right, that joins those 2 points. That's all it is. So that was exactly the rule that we wrote down before. So I tend to remember this rule, and then I would go back to use it for kind of simpler cases. Okay. There's a more complicated version of that rule. It's useful, I think, to some extent. It's especially useful for this statement. But if I were to be really precise about when this is an equality versus a containment and other things, I think it would just kind of slow us down a bit. But we can state it maybe as follows. If you have a maximum over m functions, but over any number of functions. So here S is just an arbitrary set. Okay, I'm taking the pointwise maximum of functions fs of x over, this parameter s lying in a set capital S. First of all, again, according to our rules for convexity, we know that this function is convex even if this set S was infinite or uncountable or just some arbitrary set. And we can kind of write down subgradients for this function. And it's just that in some cases we may actually be leaving some out. So here I'm telling you that all these are all valid subgradients of the function f, but there could be others under some, in some cases there could be others that we haven't written down. And it's the same essentially formula as before. I just take all the parameters s for which fs at x achieves the maximum, take their subdifferentials, take their union, take the convex hull. But because this is a convex hull of an infinite number of things, that may not be closed. Remember, you had some exercises on homework 1 where you drew some counterexamples of where convex hulls weren't closed. And because the subdifferential is always a closed convex set, I take the closure of the convex hull. So it's just the smallest closed set containing this guy. And that gives me subgradients. Those are all valid subgradients, although I may actually be leaving some out. That's the general pointwise maximum rule. Okay, if you're interested, you could come find me after class, and I could tell you some regularity conditions on these. So that set f, that set S, and these functions fs for which this was actually an equality. One important case in which we do get an equality is for norms. So we'll talk more about these dual relationships with norms as we cover duality, but I'll just point out for now, if you ever have any two values p and q that are larger or equal to 1, and they're complementary in the sense that 1 over p plus 1 over q is equal to 1, then I can always express the p norm in terms of the q norm. And in fact, in this formulation, the p norm of x is equal to the maximum over all points z, for which the q norm of z is less than or equal to 1 of z transpose x. So that's actually a special case of, so this guy is my f of x. According to that formula, I'm writing it as the max over all points z such that z q is less than or equal to 1. This is like my S. This is like my capital S, the set of all z's for which this is true. And then this guy is like my f sub z of x. Okay, that's like a special case of that rule. And what I'm told is that I look at all points z at which this is maximal, this is biggest over the set, and I take the subgradient of those functions with respect to x. What's the subgradient of, say, this function with respect to x for z being a constant? Subgradient of z transpose x with respect to x. yeah, it's just z, right, or z, depending on whether you're Canadian or American or British or something. And so what I'm supposed to do is take all those points z, take their union, and take their convex hull and take their closure. And that gives me the set of subgradients. But if you kind of work through that, you would still nothing more than just all points z to just maximize this inner product over the set. Right? Because the subgradient then is z, and because this is linear, doing the convex hull and the closure do nothing. So it doesn't kind of give you anything more. So we're just saying that the subdifferential of the p-norm is just the points that maximize the inner product with x over all points that have q-norm less than or equal to 1. So that's a very useful property. You can, if you wanted to, you could actually derive all these results, these guys, for example, and results for other norms as well from this property. Right, so let's just do that in our head. When p is 2, what's the complementary value of q? It's just 2. So I have to look at all points. So if you ask me for the subgradient of the 2 norm at the point x, then I have to find all points z that maximize the inner product of x subject to z having L2 norm less than or equal to 1. So that's just going to be the scaled version of x, right? X over its norm when x is not 0. And when x is 0, it's just anything that has 2 norm less than or equal to 1. So that was a way of establishing that subgradients for the 2 norm earlier. You can do the same thing for the 1 norm if you want, in which case you take p as 1 and q as infinity. See what that will give you. Okay, we're just about 5 minutes left, so I think I'll just maybe do this last little bit on why do we care about subgradients so much. So there's kind of 2 reasons, and next, or whenever we get to it, maybe a bit through next lecture, we'll talk about the optimization aspect of subgradients, which is that if you can compute subgradients, then you can minimize essentially any convex function. Okay, that might be slow, but you can do it if you really wanted to. So they're extremely important for that reason. They give you kind of like the broadest hammer for optimization that is available to us in some sense. And I said before, it could be very slow, but at least it's an algorithm. Another aspect that's very important is convex analysis, and we'll kind of return to that when we talk about optimality and duality and all that stuff. But here's a little preview. For any function, convex or not, it can be the weirdest, most non-convex function you could write down. You've minimized your function at the point x star if and only if 0 is in the subdifferential of f at x star. So this is true for every function, convex or not. So just to rephrase, x star is a minimizer if and only if 0 is a subgradient of f at the point x star. This is often called subgradient optimality. Let's just jump ahead, down to the bottom. Let's note the implication for a convex and differentiable function. Well, in such a case, the subdifferential is just a set containing the gradient, right? So we're saying that you've minimized a convex differentiable function if and only if the gradient is 0. This only has one element when f is convex and differentiable. So that gives you back kind of the usual rule that you know about. Okay, let's prove it now. Just one line. If g is a subgradient, right, at the point x star, then this is true for all y, right, with g here. That's just the definition of a subgradient. G being 0 in this expression just means that f of y is bigger than or equal to f of x star plus 0 transpose y minus x star. Well, that's just f of x star. So when 0 is a subgradient, we've established that f of y is bigger than or equal to f of x star for all y, which means that x is a minimizer. When x is a minimizer, clearly this is true for all y. So 0 must be a subgradient. That was both directions. Okay, so we've proved this. I think oftentimes people forget this, and they think that it's only true for convex functions. And when I kind of emphasize that it's always true, I get some surprised looks. There's really something I think very surprising about this, and that similar statements we'll make when we talk about duality in the KKT. We can make broad statements for many different types of problems, both convex and non-convex. The caveat, of course, is that either for non-convex functions, we can't compute subgradients or they don't exist. So this doesn't give you a recipe for kind of how to solve every problem, right? Because for non-convex functions, they don't always exist. So let's go back to these two functions. What are the implications for these two functions? Either of those functions of that statement. There's no implication whatsoever, right? Because these don't have subgradients, right? And there's no minimizer either. So that's fine. We haven't kind of achieved reached a contradiction at all. So for some non-convex functions, we won't be saying anything about them at all. But it still is a statement that's universally true. Okay, probably a good spot to end. On Wednesday, we'll come back and finish up our bit on subgradients.